equals, let's say, 15 degrees. Or that would be pi over 12 radians. Okay? And then maybe from here to here, that would represent phi equals pi over 4 or 45 degrees. But phi is specifically defined to start at the positive z-axis. Phi doesn't exist on the xy plane until you get to, until you get to phi equals pi over 2. Phi comes off the z-axis in any direction at some angle. Because you can take your joystick and tilt it any way you want to. I can tilt it this way, I can tilt it that way, I can tilt it toward me. But if I want to tilt it through a 15-degree angle, that's using phi equals 15 degrees or phi equals pi over 12 in any direction off the z-axis. So phi equals 0 is due north. Phi equals pi over 2 would rotate all the way down to the xy plane. Okay? Now, are there any restrictions on the polar variable theta? Can theta go from 0 to 4 pi, for example? Yeah, because you can talk about multiple rotating. Well, let me say this. If we're talking about limits of integration, using theta from 0 to 2 pi is the same thing as theta going from 2 pi to 4 pi, or from 4 pi to 6 pi, or from 6 pi to 8 pi, you see. But phi has a domain restriction on it, has certain geometric restrictions on it. Phi only exists from phi equals 0 to phi equals pi on the south end of the globe, the negative z-axis, okay? And see, theta is versatile. Theta can go negative. You start, if you're in the xy plane and you want to go clockwise, you use theta equals negative pi over 2. You want to go counterclockwise, theta equals positive pi over 2. So theta can, be negative, be positive, can go beyond more than one revolution, but phi has a restriction on it. Phi only exists from phi equals 0 to phi equals pi. So you can never talk about phi equaling negative pi over 4 or phi equaling 360 degrees. You said, yes?
Does that mean that phi is always going to be greatest second to theta?
Pardon? Is phi always going to be?
So think about it. If theta goes all the way around like this, you can really only go 180 degrees without it crossing back over each other.
Right. Oh, okay. And that's kind of why you said no. Because you don't want it to start going back over itself. Okay, so if we're applying the logic of just integration limits, you don't want your angles to overlap itself.
I guess you could do it.
So you can still use theta. Theta can go from negative pi over 2 to 0 to pi over 2 to pi to 3 pi over 2, and that would represent the same thing as 0 to 2 pi. Okay, but phi, by just definition, if I want to locate any point on this, or if I want to locate any one of these lines of latitude on a sphere, regardless of what point I'm on, if I tell you to go to phi equals pi over 4 or phi equals 45 degrees, just that alone means, well, I could rotate to 45 degrees there, rotate to 45 degrees there. It's any point on this sphere that is 45 degrees off the due north positive z-axis. Okay, so phi, if you start saying phi goes from 0 to 360, you're starting to overlap points on the sphere. So if you're locating any pitch off the z-axis, you want to say phi equals 0 is due north, and then any point on that spherical globe could say, phi goes from 0 to pi over 4 to pi over 2 to 3 pi over 4 to pi, and then in all directions that would cover any point on that sphere, at least in terms of lines of latitude like this.
So sorry.
Yeah.
You said phi is from 0 to 90 degrees?
Pi. Phi equals 0 is due north. Phi equals pi is 180 degrees away from that. Yeah.
Okay.
And then what would your lines of longitude be here? Like if I...
That's your theta.
That would be your thetas, yeah. If I put the lines of longitude in here, well, let me dot them. So it looks something like this. Just like you see on a globe. Like maybe from here to here, that's theta equals 30 degrees, or theta equals pi over 6. So if I wanted to use this as like a rho, theta, phi coordinate system, if I want to locate the point, well, given that I've only got a sphere of radius 6 graphed here, I'm pretty much limited to using a rho value of 6. Okay? And then I wanted to use a theta value of, let's say, pi over 3, and a phi value of pi over 4. And I'll guarantee if I ever prompt you for a phi theta coordinate, I'll make sure that I put the generic labeling here so you know who's playing the role of the radian measure. Because without that there, you're like, who's the phi, who's the theta? So that way you know the middle one's theta, the last one's phi in this context. Because sometimes you may see that flip-flopped. You know, you may see phi here and theta there, but I'll make sure you know who is who. So you're already on a sphere of radius 6. Any point on this is a rho value of 6, guaranteed. But now we want to cross-reference it with a theta value of pi over 3. So pi over 3 is about, let's see, from here, that's almost pi over 3 right there, because pi over 3 is about 60 degrees. So if I went for, you know, this is maybe the 0 line of longitude, and then maybe that's 15, maybe that's 30, then 45, then 60. So maybe that's the pi over 3 or the 60 line of longitude for these lines. And then I'm already on a sphere of radius 6, so I'm guaranteed to get a rho value of 6. But then I want to cross this with a phi value of pi over 4. So along that line right there, going up this spherical shell, here's phi equals 0. Phi equals pi over 4 would be, well, roughly halfway down there. So to locate that particular point in space, I'm on a sphere of radius 6, so rho equals 6. I've rotated from the positive x-axis to 60 degrees off the x-axis here, and then I stay on that spherical shell until I come off from phi equals 0, phi equals, you know, pi over 6, then pi over 4. I stop right there. That's the point that would describe in space. So it's almost kind of like you're thinking of three-dimensional polar coordinates, but you need more than one angle locative. You need more than just theta itself. Theta, like I said, is sort of like the way you'd rotate your joystick, and then once you know how you want to rotate it to, then you pitch it off the vertical axis by the angle phi, and that locates that particular point in space. Okay? So if you could make spherical graph paper, it probably looks something like this. But we can't really have something like that because it's three-dimensional. You know, you kind of have to have that floating hologram technology that they use in Minority Report, and, you know, Tony Stark throws around images with in his lab and stuff. So you could make a big row of radius 20 and a small row of radius 3, and, you know, compare the two. So eventually, I guarantee that's gonna show up the year after I retire.
Probably.
Well, then why not start at UT and research
Start
it yourself?
Yeah, start making holograms. Yeah, I've seen the the rough holograms they're making nowadays. You have to use little mist fields and stuff like that, so you stay at least cooled off a little bit. But anyway, that's as long as I can draw pictures and I don't lose the ability to draw, I think I'll be okay in terms of explaining. So that's how the spherical coordinate system works. Now, the conversions. If you want to see how these conversions are derived, I'll be more than happy to show you where they come from. Math majors out there? Potential math majors?
I'm going to take a math course every semester on college.
If you're curious to see where those come from, I will gladly stay after class and derive them for you. Okay? Because they're kind of less than obvious. They're not exactly obvious. Not just math majors, excuse me. I don't mean to dismiss the engineering or computer science folks in the room. If you want to see where these conversions come from, just stay after class and I'll go through an explanation of how you derive these spherical conversions, because the geometry is really awesome. But when you're converting between spherical and cylindrical, or spherical and rectangular, these are your XYZ counterparts, okay? You use rho, you use phi, you use theta to make these compositions in terms of x, y, and z. So just like in polar, if you need a replacement for x, you replace x with r cosine theta. In spherical, if you need a replacement for x, you have to unfortunately replace it with rho sine theta, no, sine phi, cosine theta. See, I have to go through the derivation to commit them to memory, because I've never committed them to memory because I can derive them. You have this. Remember, I've kind of made the analogy that rho represents the radius of a sphere. So if you're on a sphere, x squared plus y squared plus z squared equals 4, you're on a sphere of radius 4, that's the same thing as rho squared equals 4, or rho equals 2. So you really do want to think of rho as a sphere's radius out there in space, like a three-dimensional polar R, going in all directions, okay? Then when you're converting between rectangular and spherical, there is an integration compensator, there's a Jacobian. Just like the little R that you have to do for polar or for cylindrical, the compensator here is rho squared sine phi, okay? That I probably won't derive for you. I'll be glad to derive these for you, but that one's a hot mess, okay? I'm going to go say that one's beyond the scope of the class. So let's just stand on the shoulder of the giant that gave us that and appreciate it here and now for what we need it for. Some more equations. Spherical is really kind of handy, but it's not as, I guess, versatile as cylindrical coordinates. But you know, some of these equations turn into really nice objects when you look at them in spherical coordinates. For example, this one. If rho is the radius of a sphere, and this rectangular equation represents all the points on a sphere of radius 5, what would this translate to as a spherical equation?
Rho equals 5.
Rho equals 5. I mean, just go to the conversion formula. You can replace x squared plus y squared plus z squared with rho squared. So just making that basic replacement. This becomes the spherical equation, rho squared equals 25. And yeah, just take your square root. No plus or minus needed, keep it simple. Because in all honesty, I'm not sure if you can do negative rhos. I know negative r, remember I told you about negative r, it takes you to the polar opposite side of the polar grid, remember, for negative r values? I think rho is always positive. I think. I've never heard it take negative values, but all the rhos I've ever seen are always positive values. So that's why I don't either use the plus or minus, I just say the positive square root of 25. Boom, there's our rho equals 5. Now, this was a fun one. What would the equation of a cone be when you convert it to spherical? Remember the handy geometry about that cone I mentioned earlier. Right here. Okay, so if I want a spherical equation that represents any point on this cone, so in other words, is it true to say that all the points on this cone represent any point above the xy plane that's 45 degrees off the z-axis?
Yes.
Can you imagine what that spherical equation would be?
2. No.
Notice your rho values. Rho values would represent, radii coming out of the origin. And if it's every point on the cone, rho would go from 0 to infinity. So it's independent of rho. It goes all the way around the z-axis, so it's also independent of theta.
So your 5
So the
is going to
only-
be pi over 4.
Say that loud and proud.
Your 5 is going to be pi over 4.
Phi equals pi over 4. The equation of that cone in spherical coordinates is phi equals that constant. Probably the coolest conversion there is. Now, if you think I'm pulling your leg, if you think I'm, trying to lay one over on you, if I actually took these conversions up here, replace the x, the y, and the z with their counterparts. You want to see it?
Mm-hmm.
You know you do. All right. So replace z according to. Now this is pro bono. You'd have to write this one down. Replace z with rho cosine phi equals the square root of. Replace x with rho sine phi cosine theta, and keep in mind it's being squared. Plus, y gets replaced with rho sine phi sine theta. Okay. You think I'm in for a big old, torture chamber here, because how the heck is that going to turn into phi equals pi over 4? Promise it does. One thing that might be handy to do is to square both sides. Maybe. I probably should have written it that way to begin with without needing that big square root. But let's just look at all the algebra you can do in here. You can factor something out of this.
Rho squared.
You can-
Squared. Sine squared.
the
sine
rho squared.
Phi.
Rho
Rho
squared.
squared. Sine squared phi.
Yeah, sine squared phi is common to both of those. And notice the love you
And
get.
then you get 1 square root of 1.
Yeah, you factor out that rho squared sine squared phi, and then pardon my abbreviation, but you get cosine squared theta plus sine squared theta left over. You see, from this and this. That,
Oh, well.
also known as 1.
Wait.
And then you can take the square root of these factors one at a time, so they become rho sine phi. And all the while, you still have rho cosine phi on the left. Hang in there, it's not that bad. Most audible sigh I've ever heard. And then you wanna come up with some kind of relationship that this fixes. Okay. Well, a handy thing, you can divide both sides by rho. And divide both sides by cosine phi.
Tangent
So you get a single equation that says 1 equals tangent phi. Now, remember, what are the limitations on the angle phi?
Is that tangent or, because I thought cosine was sine. Oh, you just.
Yeah, I'm dividing this, so that becomes 1.
Okay, I was going.
So that's
the other
that's my
direction.
division symbol. Sorry, the old school elementary school.
No,
division symbol.
yeah, I just did it in a different direction. You did,
Oh,
and I ended
okay.
up with cosine phi over sine phi.
Well, cotangent equals 1.
Cotangent, that's.
Cotangent. So you could have tangent phi equals 1 or cotangent phi equals 1 because they'll be the same at that angle. What were the limitations on the angle phi? Phi only exists between
0 to pi.
0 to pi. So between 0 and pi, what's the only angle that gives you a tangent ratio of 1? A pi over 4. So in other words, if you just take the inverse tangent of both sides here, inverse tangent there isolates phi by itself. Inverse tangent of 1 is a 45-degree angle. So I'm not pulling your leg. That's why it was handy to know that that cone makes a 45-degree angle off the z-axis, because it turns into the sweetest equation ever when you put it in spherical. No x's, no y's, no z's, just pi equals pi over 4. So therefore, if I wanted a cone that pitches 30 degrees off the z-axis, be a little bit steeper, because it's 30, keep in mind this is 30 degrees off z, not 30 degrees off xy plane. So 30 degrees off z will be a little bit steeper than this cone. So that equation would just be phi equals pi over 6 for all the points on that cone that's 30 degrees off the z-axis. Okay? What's the equation of the xy plane in spherical? Phi equals pi over 2. Because any point on the xy plane would be at an angle of pi over 2 off the z-axis. Kind of like imagine taking that cone and widening it out until it's just flat, so that you get all the points on the xy plane at phi equals pi over 2. Kind of cool. All right. Let me see. Based on the time, well, we got a half an hour left. I should give you a good amount of stuff for spherical coordinates. So here's another one where you're asked to describe the region. I'm probably not going to necessarily ask you to do that. Evaluating the integral still works the same way. Keep in mind, if it's described as a volume integral in xyz coordinates, the integrand is 1. If it's a volume integral in cylindrical coordinates, the least integrand you'll see is r. If it's a volume problem for spherical coordinates, the least thing you're always going to see is that integration compensator called Jacobian. So this is technically the spherical version of the number 1. Because if you're in spherical coordinates, you have to at least have that rho squared sine phi, its version of the extra r from polar, to do any kind of volume problem. So you'll never see a polar, cylindrical, or spherical area or volume problem that has just a 1 inside there. You always at least have that r or the rho squared sine phi. So this is a volume problem because that's the spherical version of the number 1. And then integrating it works the same way. If you integrate rho first, and my rows look like p's, I'm sorry, but it's just the way it works out for me. So integrating this with respect to rho, 1/3, rho to the 3rd, just like any other triple integral. Just follow the integration order that's suggested there by the differentials. And then you plug in your 3. 3 is the only non-zero contribution layers, but gives you 9 sine phi. Next up is theta. So since theta's limits are from 0 to pi over 2, and there's no dependence on theta here, it's technically that times theta, plug in the pi over 2, subtract the 0, so just like always. Or like I'm trying to help you to remember it. That just means multiply the pi over 2 times what you got. You see? And then integrating this lastly with respect to phi, you're going to get a proper antiderivative you need to remember, because given that spherical coordinates have that Jacobian, that integration compensator of sine phi, you're always at least going to have to integrate sine phi to become negative cosine phi. And you're going to need to recall some unit circle values, because you need to evaluate the cosine of pi over 6 and the cosine of 0. And the cosine of 0, 1. Keep in mind, watch out for the temptation to wipe everything out.
Pi over 6 is square root of 3 over 2.
And yes, Yes. Sorry, you put me on the spot there. So negative 9 pi over 2. Cosine of pi over 6 is root 3 over 2. Cosine of 0 is 1. So it looks like you get a negative answer, but it's not. Square root of 3 over 2 is about 0.8 something, I think.
0.866.
So yeah, 0.866 minus 1, that's negative inside the parentheses times the negative in here. So if you want to make it look a little more normal, I guess you could take the negative from out in front of the 9 pi over 2 and reverse the order of subtraction inside there if it so pleases you. Okay, so it's still it's guaranteed to be a positive answer. But let me see if you can try to envision this. All you need to do is translate this. Let me go up here to the top of the problem. Rho goes from 0 to 3. So just that. Now keep in mind, this represents every value in space that goes from the rho value 0, and rho equals 0 is located where?
Origin.
Origin. Because keep in mind, rho comes out where like the koosh ball. You know what a koosh ball is? Is that a dying reference?
No,
Don't know what a koosh ball is.
With the
It's
rubber
one of those
bands,
little
all the
rubber
rubber
bandy
bands.
kind of things. Those little balls that have the rubber bandy sort of things kind of exploding out of it.
Mm-hmm.
So I need to actually have a koosh ball in hand when I teach spherical coordinates because some people don't even know what a koosh ball is.
I know what you- I know
But yeah,
exactly
it's
what I know what you mean now.
they were kind of popular about maybe 15 or so years ago.
Yeah,
Now,
yeah.
I guess y'all are too young to remember that.
No.
But yeah, everyone's seen fireworks. So when you see the big spherical explosion, that's your rho value. So every value of rho between 0 and 3 omnidirectionally represents what?
The radius
Of
of
a
the sphere?
sphere, not just the surface, but every rho value between 0 and 3.
The entire volume.
So the solid interior of a sphere of radius 3, not just the boundary, because rho continuously changes from 0 to 3. Okay, so it's every point on and in a sphere of radius 3. Then you cross-reference that with this. Theta goes from 0 to pi over 2. So just 0 to 3 for rho gives me a full three-dimensional sphere of radius 3. Crossing that with 0 to pi over 2 for theta,
It's just the top hemisphere.
for theta.
No, it's just the
Oh,
first
theta.
octant.
Pi over-
Yeah,
Is it-
theta going from 0 to pi over 2 is not just the first octant. Well, you've already looked at this. So just disregard the 5 for a second. So we've got a full sphere of radius 3. Beginning at theta equals 0 to pi over 2, that takes 3/4 of the sphere away. So essentially you've just sliced an orange and you have a quarter of the orange from top to bottom. But then cross-reference that with your phi. Phi equals 0 begins where in my little quarter orange?
36.
At the top. And I pitch how far off of it?
1/3 of the way through that.
30 degrees-ish, well, no, exactly 30 degrees off the z-axis. So if you have that quarter of an orange that you've sliced this way for theta equals 0 to pi over 2, I know I'm doing this like I'm holding something actually in space, and then I pitch it from 0 to
Like
pi
a
over
slice
6,
of pizza with the
it looked kind of like this. Let's see. Something like that, maybe.
Okay.
yeah.
Kind of sucks, but
So if phi was negative, you can pitch from the bottom up
phi is not negative. Phi can only exist between 0.
in pi. Oh,
Pi.
so it would start from pi.
Well,
oh,
okay,
I guess the range.
what if?
it would be from like pi over 2 to pi or something.
Okay, so if you wanted the bottom half of the orange,
Right.
3
phi equals pi over 2 to pi would give you the bottom half of the
Okay,
orange, that's
yeah.
right. What if I wanted the bottom 30-degree section?
Be 5 pi over 6 pi.
5 pi over 6, 150 degrees to pi, 180 degrees. That would give you the bottom 30-degree section off the negative z-axis, you see? So you gotta remember your 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. You just need those first and second quadrant angles when you're dealing with phi. Alright. Let's see. This one's pretty easy. Here's a convert from rectangular to spherical. You're doing the triple integral over a three-dimensional volume of this function. Works really well with spherical coordinates. Where E, the solid region you're integrating over, is a sphere of radius 3 centered at the origin. The full sphere of radius 3 centered at the origin. So, integrand first. integrand is x squared plus y squared plus z squared raised to the third. That converted into spherical, I'd like to think is pretty smooth. As long as you gotta sort of make this also one of your paradigm shifts. Spherical, or well, cylindrical and polar, the main pairing there is x squared plus y squared equals r squared.
Yeah.
Go one dimension higher, and that's why I kind of want you to think of rho as like a three-dimensional spherical version of r. So anytime you see the expression x squared plus y squared plus z squared in either the limits or in the integrand, that directly translates to rho squared. So as my spherical conversion, what's in the parentheses?
Rho to the fifth.
Well, be careful. A power to a power, you multiply the exponents.
Okay.
Yeah. So in that case, that would be rho to the sixth.
So it's rho to the eighth sign?
Yes. So considering the Jacobian, since that's your integration compensator, the proper integrand will be rho to the eighth sine of phi. Okay. Now, what would your limits need to be? Let me go ahead and put my integrals up here. We've already figured out the integrands, rho to the eighth sine of phi. And I'll stick to the same order we had up there. D rho, d theta, d phi. My phi's are sucking tonight. Okay. Okay.
So 0 to 1 for rho.
Well,
0 to 3.
yeah, solid sphere radius 3, center of the origin. So there's your rho right there. Rho goes from 0 to 3, every point in and on a sphere of radius 3. And it doesn't mention the first octant chunk. So what would your theta limits be?
0 to 0 sign.
All the way around for every line of longitude. So 0 to 2 pi for theta. So that covers the radius, 0 to 3, that covers going around in terms of our longitude lines. But what part of the latitude do I need it? 0 to, no,
0
I
to
need
pi.
0 to pi. I want the full sphere. So phi needs to go from the North Pole all the way to the equator at phi equals pi over 2 to the South Pole where phi equals pi. So to cover everything in terms of lines of latitude, you want phi to go from 0 to pi. So you need every phi value for all your latitude, you need every theta value for all your longitude, and then you need everything from the core of the Earth to the surface of the Earth, where the radius of the Earth is 3. Small Earth. Okay? So that we'll just do that one as a conversion problem, because integrating it now, you've got powerful negative cosine phi pops up, and you'd eventually need the cosines of pi and 0. So I think this one turns out to be pretty sure this one turns out to be a positive value. Bless you.
Okay.
So let me see. I've got 2 more examples here, and actually this one's the fun one. I'll come back to that one here in a second. Oh, we got out of place. This one comes with a picture, and given that, I'm going to want to probably give you pictures whenever you're dealing with some of these integrals. Let me go ahead and introduce you to some of the other graphics you might see. This is an object we're going to want to find the volume of for some reason. Maybe it's some kind of machine part. We need to figure out what the cubic capacity is for a production process or something like that. It sounds really official when I describe it like that. But we just need that thing's volume, okay? Triple integral in rectangular coordinates for the function 1 gives you a rectangular volume. Translating that to spherical, remember, you got to at least have that Jacobian rho squared sine phi in there, and it's still calculating a volume even though you're in a different coordinate system. So the region here is the solid that's lying inside the sphere of radius 8. So right there, if I pitch that all the way down to the xy plane, that is a radius of 8. Well, I guess I could do it here too. All right, so there's a radius of 8 on that sphere. It's everything that's, I guess, inside and on the sphere, so it's solid. There's stuff inside there too. Also lying between the cones, which make a 30-degree angle off the positive z-axis. So over here, in positive z, when you pitch to this first little core that's cut away, that's 30 degrees off the z-axis, and then everything between there and 60 degrees off the z-axis is included. So, and here's a cross-section of it to show you that, the inside workings, where the 30-degree cut's made and where the 60-degree cut's made goes all the way down to the origin, kind of like this. Although this is a misleading image because you can see the little kind of gap right there. It's supposed to be solid when you see the cross-sectional section of it. Okay. So, setting up the limits that would represent my volume. Take a minute, because you've only got a minute, to set up those limits. Already done it? Pretty straightforward. The picture helps out. But heck, I mean, I guess the verbal description is also pretty cool too. You can probably get it just from there. There, my fives are getting better. Okay. Your row limits.
0 to 8.
0 to 8. Every point from the origin outward to that sphere radius 8, so that's pretty straightforward. Your theta limits
0 to 5.
sweeps all the way around in that direction, so that's your most popular theta choice is from 0 to 2 pi. Your phi limits, I guess, are the main thing you want to pay attention to. Pi over 6 to pi over 3, yeah. Pi over 6 is 30, pi over 3 is 60. You ever notice how the 6 and the 3 kind of swap out there?
Yeah.
That's the way I committed it to memory. So pi over 6 is the beginning value of phi where this region exists, and this region ceases to exist once you pass phi equals pi over 3 off the z-axis. Okay? That's it. Does it seem pretty easy?
Not bad.
Let's look at some of the homework problems I assigned. Oh wait, where did it go? No. Where's the spherical suffering problems? They should be here. They're I mean, have you printed those off chance? The stuff for spherical and cylindrical? Are there none?
I think there is a package that's separate from those.
Oh shoot. Because that's just the notes, and I thought the problems were at the end of it. Bear with, oh shoot, that's your test. Close that. Wait, what changes did I make? Save changes? Holy, I don't remember making any changes. No. Now I'm gonna panic. What changes did I make? Okay, don't save. Alright. Oh, and I told everybody about the last problem on the test. The last problem is currently worded as convert to polar and evaluate. Don't evaluate. Just convert the double integral to polar, and that's the only thing I'm gonna grade you on in the last problem, number 10. Okay? If you want to evaluate, you're welcome to, but you know, yeah. I'm just looking for the polar
Get
conversion.
bonus points if you get it right.
Yeah, we'll see. So I want to pull up, and I know I've got some problems here that represent, I've done some supplemental problems before. Go to my drive, my 2110 stuff, my blank notes. I know I've got double integrals, triple integrals. Okay, there it is. Cylindrical, spherical, supplemental homework. Let me show you. So this will be posted on D2L. There are some other things I added to D2L today. Because currently all you had up there was up to triple integrals and spherical and cylindrical. I've added the rest of the stuff that goes over vector fields, the surface integrals, the line integrals for the last chunk of material for test 4. That is there now for your blank notes to print off. So these are some of the problems I've got for cylindrical and spherical. And I've got them separated. The first 6 are devoted to cylindrical, the last few are devoted to spherical. That's a pretty lame picture, but you can tell that was running paint. So, and you know, there's a few where I may probably should have put a picture in here, but I didn't. Like this one. Well, I don't know. You may not need, sorry, the hand's in the way there. But you may not need a picture for this one, because this is one where you're just converting from rectangular